Okay, good afternoon, 61C. Can you hear me? Hey. Is this mic on? Can you hear me? Yeah. All right, great. Okay, so last time we were looking at how to build different components out of logic gates. We're going to do a bit more of that. Then we're going to move into like the sort of really the heart of the course, which is how do you take these physical devices and build a processor, a computer that can actually run any program you could ever write. The one we'll do in this lecture and next lecture is a very simple little processor design, but it can run any function you could imagine. Anything that can be computed, this thing can compute. And it's always amazing to me how little you need to actually run software in hardware. We're going to go over that in the next couple lectures. So just to remind you what we looked at last time, remember all the systems we're building are synchronous digital systems. They're synchronous because there's a clock that tells everybody when to move to the next cycle and take a snapshot of their inputs on the registers, produce it on the outputs. And around those clock edges, there are these constraints, all the physical circuits, these registers have to observe that the signals that arrive, they have to arrive at least a setup time before the clock edge to allow the input to settle. You then have to hold the signal stable for a little while after the clock edge. And this is to ensure that you can reliably capture the signal at each register when the clock edge arrives. And then there's this notion of clock to Q time, which is really, it's not about correctness, it's about timing. Like from when the clock arrives, how long does it take for the new data to propagate to the output of the register, which is Q. So that's why it's called clock to Q time. We talked about muxes, and as you'll see, muxes are the most common component in a computer, probably apart from the registers themselves. And in general, a mux takes some number of inputs and a select input, and the select input says which one of those inputs should be connected to the output. We looked at building muxes different ways, either just flat, where all the inputs were selected at once, or hierarchically, where you had stages of mux to select an output. Then we also started looking at how to do an ALU, and so today we'll finish that off, how to build an arithmetic and logic unit, which is the circuitry that provides the basic functionality of doing an add, or doing an XOR, or an AND, or a shift circuit. Okay, so let's dive straight into that, how to design an adder or a subtractor. So any combinational circuit, you can always describe it as a truth table where you lay out exhaustively for every combination of inputs, what should the output be. However, when you have something that has many, many inputs, like an adder that adds two 32-bit numbers together, you have an infeasibly large number of rows in that table, right? So it'll be 2 to the 64 rows, which is many, many, many rows, right? You'd never get through that table. So when designing something like that, the trick is to divide and conquer, break it down into smaller pieces, and then cascade them back up again to get the functionality, right? So in the case of an adder, instead of worrying about 32 bits at a time, we're just going to look at 1 bit of the adder at a time. So what does 1 bit of the adder have to do? Okay, so in particular, we're going to start with the easiest bit, which is the least significant bit. So I have 2 numbers here. These are 2 4-bit numbers, A0 through A3, B0 through B3. And if what I want to do is reduce this sum, S0 to S3. So remember, I'm trying to build a combinational circuit that will take these inputs as signals, and after some propagation delay, the output will settle to the sum of the inputs. To break things down, make it easy, I'm just going to look at 1 bit now. And to make it very easy, I'm just going to look at the first bit, the lowest bit, the bit that has the least significant value, like bit 0. Okay? So now all I need to worry about is I only have 2 bits, so I only have 4 rows in the table. For each combination of these bits, what output should I produce? The obvious output is the sum output. So what's the least significant bit of the sum given the least significant bit of the inputs? Okay, that's this column. And so you see that if both inputs are 0, the sum is 0. 0 plus 1 is 0. 1 plus 0 is also, 0 plus 1 is 1. 1 plus 0 is 1. Now 1 plus 1 is? 1 plus 1 is? Great. So what's the least significant bit of 2 in binary? 0, right? So it's 2, which doesn't fit in 1 bit. Okay, so you have 0 for the low bit of 2, and you have a carry out, which is the high bit of that 2, right? Now, when you're doing addition longhand this way in decimal, you all know how to add a column of numbers and carry into the next column. You do the same thing in binary. So if I add 2 bits here and get a sum that won't fit in 1 bit, I have to carry the other bit across. Okay, so that's the carry out from that bit position. So, and this is the truth table for the carry out. Only if both bits are 1 do I get a carry out, which I feed into the next column. Okay, so the least significant bit was the easiest bit because there's no carry into that position, right? It's where you start from. You start at the least significant bit and propagate your carry up to the higher order bits. So now notice we have the truth table for the least significant bit of the adder. So that lets us go ahead and write down the logic equations for that. And we can simplify them down and see that, well, actually, the sum bit is just the XOR of A0 and B0. Remember, XOR is exclusive OR, so it's true if one or the other, but not both, are 1, okay, an exclusive OR. So S0 is A XOR B. Now the carry is only a 1 if both A and B are a 1. So it's just simply the carry out is A and B, A0 and B0, okay? So that's the logic expression for the low bit of the adder. Now let's move up a bit to the next bit of the adder. So now life is more complicated because we actually have 3 inputs. We have the A1 and B1 from the numbers we're adding, but we also have to factor in the carry coming from the lower bit coming in. So you have the carry in here, and at this bit position we also need to produce the sum, but we also need to produce the carry out that's going to go to the next position along. Okay, so if we drew the truth table for this adder, first thing is now there are 3 inputs, so now there are 8 rows in the truth table, and for each combination we can fill in what the sum and carry out should be. So just to pull out a few of these, so if everything's 0, the sum will be 0 and the carry out will be 0. If A and B is 0 but there's a carry in, the sum will be 1 and the output will be 0. So notice you're adding 3 1-bit values. So the sum plus carry, informally the value is going to be somewhere between 0, 1, 2, or 3, depending on how many 1s you have in any row of this table, right? So there's 1, 1 here, there's 1, 1 here, there are 2 1s here, so it's 0 plus the carry out. There's 1, 1 here, 2 1s, 2 1s, and finally this last row, all 3 are 1. So 1 plus 1 plus 1 is 3, right? So sum 1, carry out a 1, okay? So that's 3 in binary, right? The carry out of that bit position goes to the next bit position. So now we've written out the truth table for this middle bit of the add, and we can translate that directly into logic equations. And if you notice, this sum is actually the XOR of all 3 bits. So basically, if there is an even number, it's 0. If there's an odd number, it's 1. Okay? So if there's an odd number of bits, that's when you do the XOR. It's basically odd. If there's an odd number of bit set, it's a 1. If there's an even number of bit set, it's a 0. The carry out is what we call a majority function. That's really just, are there at least 2-bit set, right? Or at least 2 out of 3 of the bit set. That's what it means by majority, right? 2 out of 3 bits, are they set? If so, and then you can write that out as a logic expression if it's A and B, or A and C, or B and C. Any 2 out of the 3, if they're set. Why don't I have or A and B and C? Why didn't I add that to this logic expression? Right, it's already captured by, if any 2 of them are 1, it doesn't matter if I OR in and all 3 of them are 1, right? So any 2 of them are 1. You don't need to write that out. It's an example of simplifying the logic expression. So I can actually draw the logic gates for this now as well. So this is the symbol for an XOR gate. It's like an OR gate, but with an extra line here. So 2 lines at the input. So if there's an odd number of bits in here, you get a 1 on the output. If there's an even number of bits, it's a 0. And this is the network for this expression. So A and B in this logic gate, B and C in this logic gate, A and C in this logic gate, added together. And then you OR together all these 3 to give you the final carry outputs. That's just the logic gate circuitry for that. Both of these are logic gates you need to do the middle bit of an adder, right? So this middle bit is usually called a full adder, and the adder that starts at the LSB that doesn't have a carry in is called a half adder. So there's a half adder and a full adder. This is a full adder. Takes two inputs, a carry input, and produces a carry output. So now you have all the components you need hierarchically to build an n-bit adder, right? If you have both kinds of one-bit adder, if you want to make a large adder, you just string them all together, right? So you have, this is the circuitry for one adder. So basically, version this on this slide. A carry coming in, sums coming. I'll talk about why there's a C0 here. You don't need this for an add, but we'll talk about it later. A0, B0 produces sum 0 and carry to the next one. So these are all chained together. And just think about what happens in a circuit if you build a circuit this way. I present all the inputs. Say I present all the inputs at the same point in time. A0 through A3, B0 through B3. What's going to happen is the signals are going to propagate through those blocks combinationally. They're just going to ripple through. So remember, when I set these inputs, I throw some switches inside here that connects these outputs to power or ground, depending on the combination of these values. This input will then set the switches in here, along with the switches that are already being set by these signals. And so what will happen is this carry signal, these inputs are already right at the beginning, but the carry signal is going to slowly propagate through here, sort of flipping the outputs to the correct state as the circuit evaluates. Right, and this happens as a wave in real time. It slowly propagates through the circuit. And finally, at some point in time, the whole adder, all the output bits will be correct according to those input bits. Okay, it's a combinational circuit. Right, the signals just propagate through as a wave through this whole array of gates. And that's how you build a 32-bit adder. So there's a few other details we need to build an arithmetic logic unit. You have to worry about overflow. So what did you learn about overflow? How do you know when there's been an overflow in a sign number? Right, so when the carry in and out of the last bit are different, then you know there's been an overflow. Okay? So you just you'd have a bit of circuitry hanging off here to look at these two carry bits, okay, to tell you there's been an overflow. So that's an adder. If it's unsigned, you can just tell by there's a carry out. Now let's build a subtractor too, and it turns out there's a nice trick. Because we're using 2's complement to represent sign numbers, there's an extremely clever trick to build a subtractor. And remember, there's a trick to negate a number. What do? You invert the bits and add 1, right? So you learned that already. So you invert the bits and add 1 to get from the positive to the negative or vice versa. So the way we're going to do subtraction is take a number and add it to another number where the second number we're going to negate. So that's how you do subtraction. Instead of doing a plus b, you do a plus minus b. So I'm going to add the negative of b to do the subtraction between a and b. And the way I'm going to negate it is by inverting it. And an XOR gate is an interesting gate because it can act as a conditional inverter. Right? So remember, an XOR gate, if both inputs are a 1, it's a 0. Otherwise, it's, if one of them is a 1, the output is a 1. If both of them are 1, it's a 0. If both of them are 0, it's a 1. What it turns out is if you can look at this guy as this control signal here, if I set y to a 1, then if x is a 0, it becomes a 1. If it's a 1, it becomes a 0. If I set y to 0, it doesn't invert. You get this original value back out again, right? So you can view the second input to an XOR as conditionally inverting the first input. Okay? So all that means is when this signal is true, it inverts B. When this signal is 0, B passes through unchanged. So that control signal, I can change that line up and down to conditionally invert the bits in B. The second trick is to see that, well, when I negate a number, I have to invert all the bits. I'm not quite done yet. The next thing I have to do is add 1 to that value. And the way we're going to add 1 is by using this carry input to the lowest order bit. So we're doing an add. This line will be 0. So this line will be 0. You won't add a carry in here. And these XOR gates won't do any inversion. The value just passed through unchanged. If we want to do a subtract, we set this line to 1. That feeds a single bit into the carry input and also inverts B. So effectively then you're adding A plus minus B. So that's how you build a adder-subtractor unit. So now we're starting to get the feel of what a arithmetic logic unit looks like. It's a block that can do several functions controlled by some control lines. So this is a control line that's changing the function it performs on the inputs and outputs. So this guy has two functions, add or subtract, and this is one way of building that using a bunch of gates, all right? So notice we reuse all the adder functionality. We don't have a separate subtract circuit. It's just one adder circuit plus a layer of XOR gates to change its behavior. Okay? It's a good time to ask questions. Yep. So the question is, why does conditional OR flip the bits? Well, this is a conditional XOR. It's an XOR, exclusive OR, and this is the truth table for exclusive OR. So just step through. Let's say that X is the input and Y is the control input. All right? So then, when Y is 0, if X is 0, the output is also 0. So the output just follows X. When you set Y to 0, the output follows X. Right? When Y is 0 here and X is 1, the output's 1. But when you set that input to 1, you get the opposite of X on the output. So when Y is 1, X equals 0 means the output is 1. And when X equals 1, the output is 0. So you can view that the second signal conditionally changes the polarity of the first signal on the output. Right? Yep, question? Okay, so the overflow is, so notice, sorry, I've added a circuit, I should have mentioned this. So there's a circuit block here, just another XOR gate. So remember, XOR tells you when things are different. So the XOR will be a 1 only if the two inputs are different from each other. So in this case, the overflow bit will be set here on the output if this signal is different from this signal. If this is a 0 and this is a 1, or this is a 1 and this is a 0, if they're both the same, both zeros are both 1s, the XOR output is 0, so there'll be no overflow. So it's just that one gate that's telling you there's an overflow in the output. Question?
On real computers, do they use separate subtraction and addition circuits, or do they just have a whole bunch of subtraction?
In real machines, this is the kind of thing people do, to build an add-subtract unit, yeah. Question?
Where do you say the 1 gets added after you convert?
Yeah, the question is, where does the 1 get added? Well, the 1 is, we sneak it in through this carry input. So instead of using a reduced adder in that low bit position, we're going to use actually a full adder with a carry input that you don't need for an add, but we're going to use it as part of doing negation for the subtract. So that's why it's sort of clever hack. So there's actually no mux here. What's clever is we're using this XOR gate to flip between doing add or subtract. By optionally negating B, that's where we get the functionality of a subtract. Right? There's no mux needed because the XOR gates kind of give you two different operating modes without needing a mux. Okay? Okay, so the XOR serves a conditional inverter. Yeah, over time, as you play with circuits, you build up this library of these little tricks that people know. Why does the overflow do this? Like I explained, this is, you're checking if the carry out is different from the carry in and the high order bit, and that's what the XOR does. It sees if its two inputs are different, it outputs a 1. If they're the same, it outputs a 0. So that signal is telling you if that current value is in overflow or not. Okay, so that was some material I hoped to have covered last time. Didn't quite get there. So for this lecture, what we're going to try and do now is we've seen the basic pieces, basic circuitry pieces. Now I'm going to look through and build a whole computer in this lecture, next lecture. So the major components in a computer, we've shown this diagram a few times. The processor piece is what we're going to focus on. And this is split into two parts, called the control and the data path. The data path is kind of where all the data values live, where the registers are. In MIPS, $0 through $31. It's also where the ALU lives that operates on those wide values, the wide 32-bit values. The control is kind of what tells the data path what to do, like which registers to read, whether to do an add or subtract, where to place the results. And we'll talk about this a lot more in this lecture next. And remember, in MIPS, you also have a program counter which points to the current instruction you're executing, has the address of the current instruction. And then, of course, the processor connects to memory, where all the data lives, where you have a byte addressed array. You generate addresses that indexes memory. So the processor is electrically connected to the memory and can read and write it from given addresses. And then we have input I/O to read things from files or keyboards and output things to screens or disks, etc., right? So these are the major components of a computer. So the program and the data live in that memory, and so the processor is then going to read the memory to figure out what's the next instruction at the program counter, suddenly operate on it, and depending on the instruction, it might just do something in the registers, like a MIPS add, or it may read and write the memory if it's doing a MIPS load or store. So that's kind of the basic operation of a computer. So we're going to focus on the design of this today, how you build this processor. Oh, before I do that, quick break. So in the news, talking about processors. So I was just at there's an annual conference called the International Solid State Circuits Conference in San Francisco. It's always in San Francisco this time of year. And this is a place that companies announce big processor chips and all the details about those chips. So IBM announced their latest mainframe, the Z13, and it's quite an impressive chip. It's in 22 nanometer technology, which is the sort of scale of the transistors involved. The most impressive thing to me was they have 17 layers of metal on this chip, so that's 17 wiring layers. So the transistors are that layer at the bottom. You remember in one of the slides I showed you a few decks of wiring. This thing has 17 layers of wiring on this chip. 4 billion transistors on the chip. They actually have a cache chip that has 8 billion transistors on the chip, but the processor chip is 4 billion transistors. And this chip has 8 processors on, a little more complicated than the ones we're going to talk about today. And those processors have 2, so the cache hierarchy is also interesting. This is a mainframe, so a very big machine. We'll talk about caches later in the class, but some of you may already know, have a basic idea here. So 2 megabytes of L2 cache, 64 megabytes of level 3 cache, and 480 megabytes of level 4 cache. So that's nearly half a gigabyte of cache memory in the hardware, and there's a huge amount of DRAM main memory behind that. This thing runs at 5 gigahertz clock rate, executes 6 instructions per cycle in each processor. We'll mention a little bit about that later in the class, what that means. But the processors we're doing right now do 1 instruction at a time. This machine can do 6 instructions at the same time, and 2 threads per core. And you can put up to 24 of these chips together into one system, one very large system. And that probably costs you a few tens of millions of dollars to buy it, but that's IBM. So there's a big chip just announced yesterday, actually. Okay. But now let's go with our CPU. Our CPU is not quite as impressive, but it's really cool because you can all build it in a few weeks. And it can do anything that other computer can do, just a little bit more slowly. All right. So the CPU, the central processor unit. So this is the processor. This is the active part that does all the real work in a machine. And we break the processor down into 2 pieces. The data path, like I already mentioned, the portion that contains the wide words, most of the storage, and then the control, which is really the brains of the processor. Like the processor is the brains of the computer. The control unit is the brains of the processor, like tells it what to do. Now, in thinking about building a computer, you all now somewhat familiar with the MIPS instruction set. So those are the instructions that the hardware understands and that it can execute. And in thinking about building the hardware, you first sort of sit down and figure out what are the different phases of executing all those instructions. And for MIPS, it turns out we can break those down into 5 stages of instruction execution. So all the instructions go through these phases of execution in the hardware. First stage is instruction fetch. Second stage, instruction decode. Third stage is ALU. Fourth stage is memory access. And 5th stage is memory write. So these are the register write. These are the 5 stages all the instructions go through. So I'm going to dive through those one at a time. Now the first stage is one that every instruction has in common, instruction fetch. So remember, this is a stored program computer, so the instructions are stored in the memory of the machine, right, in the program space. So the first thing the processor has to do is read those bits from memory into the control unit so it knows what you're supposed to do next, like what's the next instruction. So this involves taking the current value of the program counter, the PC. Those bits represent an address. You send those bits across wires to the memory saying, this is the address I want to get an instruction from. The memory then takes that address, looks up those bits in the memory, returns those instruction bits to the control unit inside the processor, and it captures them inside the control unit, so then it can start looking at the bits and figuring out what it's supposed to do now, right? So that's instruction fetch, getting the bits from program memory back into the processor control unit. Also, at the same point in time, we'll actually increment the program counter and add 4 to it in MIPS to move on to the next address to get ready for the next instruction fetch. Question? How does it actually get the bits? So we'll go through that a little bit later, but basically there's a set of, say you have a 32-bit address space like we do on the MIPS you're using. There's 32 wires that carry the address to the memory chips, and they decode those 32 bits to figure out which particular cells bits are stored in, then reads the values from those bits and pushes them back on another set of 32 wires going back to the processor where it captures those values, right? So you can view the memory as a big combinational block that you send it 32 bits and tell it you want to read those bits, and sometime later 32 bits come back that represent what was stored at that address in the memory at that point in time. And the processor captures that and then starts decoding those 32 bits of signal. Now, instruction fetch, every instruction, you have to fetch every instruction, right? They're stored in program memory. Every instruction has to go through that stage. Also, every instruction, you have to decode it. So all I've done so far is get the 32 bits from memory and put them in the processor. Now I have to start the work of understanding what do I need to do by looking at the combinations of bits depending on the opcode and the funct fields or the other fields inside the instruction. What operation should I do? Is this an add? Is it a load? Is it a branch? Is it a jump? So I have to decode the instruction bits to figure out what to do. And there's some circuitry then that looks across those 32 bits in the instruction and figures out what to do. The most important one is the opcode, because when you first look at the opcode, because that tells you how to understand the remaining bits in the instruction, right? So remember, there are different instruction formats, and so the opcode will tell you what format to use and what the different fields will be in the rest of the instruction. Now, another thing we'll do during decode is figure out which registers are being accessed, and then actually go and access those registers. So, do I need register 5, register 7? Depending on the opcode, it'll tell me which registers I need to read. The other bits in the other fields in the instruction will give me the addresses of the registers, 0 through 31. I'll feed those into a circuit that holds the registers, the register file, and read the values from that register file. Notice different instructions read different numbers of registers. So some instructions read 2 registers, like an add. Some instructions read 1 register, like an add immediate, add with immediate. Other instructions read 0 registers, right? What's an instruction that doesn't read any registers? Jump, right? Jump doesn't read any registers. It just goes straight to some address. So part of decoding the opcode is figuring out which registers and how many registers do I need to read from the register file, okay? So now we've gone through instruction fetch, getting the bits from memory, instruction decode, figuring out what the instruction is going to do, and reading any register values it needs. Now we move into execution, where we actually start doing some work. And in there we'll have the arithmetic and logic unit. And so things like add, subtract, this is where the adder circuitry will live in this stage. So you fetch the operands, you've got the 2 register values, you feed those as inputs to the adder. The adder works away and produces the value you need as a result of the addition. And similarly for shifts, logic, comparisons, and so on, right? That's where the OU lives. So the question here is, what about loads and stores in MIPS? So if you look at the MIPS load and store instructions, you see that they allow you to specify a base register plus an immediate offset from the base. And you have to actually add those 2 together to get the effective address you're going to go to memory with. And so that also happens in this stage. So what happens is, for a load instruction, in the ALU stage, you will do the add to calculate the address you need, using the same adder that you used to do an integer add, right? So it's the same circuitry is used to calculate the sum of, in this case, the value in T1 and the immediate 40, and that calculates the address that you will send to memory for the load. So notice that the way the MIPS instruction set is designed, no instruction needs 2 adds, right? You're either an add instruction that doesn't touch memory, or you're a memory instruction that doesn't do any arithmetic, right? And that was a very conscious design decision so that you only need one adder in the system, in the ALU stage, right? It's either used to do the computing or to calculate the address for load or store. The fourth stage is memory access. So now, obviously, this is only done by instructions that access memory. In the MIPS, those are only load and store instructions, right? All the other instructions just do nothing during this phase, right? This is only for the loads and stores. All the other instructions don't have to worry about this stage, just loads and stores. Okay, now, we'll talk more about caches later, but for now, just assume memory is really fast. So it just takes a small amount of time to read a value from memory and get the result back to the processor. And when we talk about caches, we'll see that that's a standard architecture way of making it seem like your memory is fast, even though it actually isn't. So now we've got through most of the phases. Now the last phase of execution, we have to write back the result we got back to the registers. Right, so for example, if you did an add, you read the registers in the decode stage, you did the computation in the execute stage, and you produced the result, but the effect of that instruction should be that the result is written to one of the registers, the destination register, RD, right? So you need to write it to a register. And that happens right at the end of the execution. So register write is done by all the arithmetic operations, but there are some instructions that don't write back. Okay, so a store writes a value to memory. It reads two registers. One of them is the base address that you add an immediate to get the real address. The other register is the value you're going to store at that address. But the store happens to memory. You're updating the memory. You're not updating any register inside the CPU, so a store instruction doesn't do anything during the register write phase. It kind of already finished doing its work in the previous stage during the memory access. Branches and jumps also don't write a register. They just read the register, determine a condition, and change the program counter. They don't write a register in the register file. So they also do nothing during this stage. Okay, so all the instructions use some number of the stages. Many of the instructions don't use all of the stages. Right? So let's now look at a bigger picture of the whole data path and kind of go over how instructions flow through this data path. So what I'm showing here is I've actually split the memory into two pieces to make it easy to draw. Instruction memory here and data memory here. So in reality, in old modern machines, it's all the same memory, right? There's just one lump of memory that you can use for instructions or for memory. There are some older machines and actually some very tiny microcontrollers you can buy now that have actually physically different memories for instruction and data. But nearly all machines, these are all unified. I'm just drawing it this way to make it simple to see what's going on. So notice you have the program counter at the front here. And the first stage is instruction fetch, where you take the value in the program counter, send it to the instruction memory. And by send it to the memory, I don't mean put it in an envelope and address it. There's like a set of wires that carry ones and zeros. So the ones and zeros coming out of the program counter, those at the clock edge, you'll update the program counter. There'll be new values of ones and zeros. Those will change the values on those signals going to the memory. The read of the memory is also a combinational process. So after the inputs settle down to the memory, sometime later, this instruction memory is going to produce an instruction at its output. And that's the end of the instruction fetch phase, right? You've taken the program counter, you've read the memory, produced the bits that are at that memory location. The other thing you do on the side is you sort of increment the program counter by 4 and get this ready to be written to the PC for the next instruction fetch. Notice there's a mux here because sometimes you don't just always go sequentially adding 4. Sometimes you do a branch or a jump. So you need to worry about putting in a different value other than PC plus 4 into the PC. Okay. So this is instruction fetch. So at the end of instruction fetch, you have the bits for the next instruction sitting here, the output of the instruction memory. And there's a few fields in each instruction, which are those 5-bit fields specifying which register to read. So those are fed to the next. During decode, you're going to look at the opcode field out of here, and figure out which of these fields will be used to read the registers out. Okay, and also at the same time, you'll be figuring out how to set all the other controls in the data path to execute that particular kind of instruction: add versus jump versus load. Okay, but one thing that's happening in the data path is you're reading the registers out of the register file. So you're reading out the two operands you might need. In the third stage, you actually execute the instruction in the ALU. So all the arithmetic operations just do the computation there, loads and stores, calculate their effective address by adding the base register value to the immediate value in the ALU. Notice the ALU is being fed both by this register and by this immediate coming out of the instruction bits in the instruction word. Remember, the immediate's just a 16-bit field at the bottom of the 32-bit instruction word. So now at the end of the execute phase, you have the result of the ALU here, and then you move into the memory phase. So remember, only loads and stores do anything in the memory phase. So if you're doing a load, you're going to feed the address coming out of the ALU into the memory, and the memory sometime later is going to produce the value at that memory location, the data at that location, and return it. If you're doing a store, then the ALU is also still calculating the address, but now you need to store the data value which comes out of a register here. Notice that when you're doing a store, you need to read three things. You need to read the base address, comes out of a register, the data value you're storing, which comes out of another register, but also the immediate, which is added to the base address to give you the effective address. But that comes from the immediate field in the instruction. You don't have to read the immediate from the register file, right? That's how it kind of all works, right? And the final stage is this register write, where you actually take the result and write it back to the register file. So the result can either be the value from memory or actually this value from the ALU being written to the register file if it's just an arithmetic operation. Okay. So these are all the components and how they're animated over time during the execution of a single instruction, right? And all the MIPS instructions go through these five phases, but not all of them are active in every phase. Depends on the instruction. All right, to try and make this a bit more concrete, I'm going to do some actual examples of individual instructions. So let's do an add. So an add like this just puts the result in R3, the sum of R1 and R2. So stage 1, you're going to fetch the instruction, increment the PC. Stage 2, you'll figure out you've got the bits back from memory. You can look at the opcode and say this is an add. And because it's an add, I need to read registers R1 and R2. Stage 3, I actually add the two registers together. Stage 4, I do nothing. I'm not touching memory with just a simple add. In the last stage, I write the result into register R3. Okay, so that's how an add instruction is broken down into those 5 steps. If I then go look at on the data path diagram what's happening, so in the first phase, this add instruction is stored somewhere in memory, so there's 32 bits in memory that hold the encoding of that add instruction. The program counter is currently pointing at that location in memory, so during fetch, I'm going to send the PC in and get the instruction bits will come out of here. So here's show them what's lining up. So there's a wave of activity. The PC bits are being sent across these wires to the memory. They're also being sent into the adder circuit, so it's calculating +4 here. At the same time, in parallel, so this +4 plus access to the memory are happening in parallel, right? It's just circuitry. Parallel circuitry is doing the +4 and the memory access at the same time. So through here, I'm getting the reading out the instruction bits. So in these register address fields, I'll get 3, 1, and 2 are going to come out corresponding to these register specifiers in that 32-bit instruction format, right? So these are the register specifiers coming out here. There's also the immediate, which isn't really used here. So because I look at the opcode, I can tell the register file you should be reading R1 and R2, these two registers, and they'll appear as 2 separate outputs of the register file. So the register file lets you read 2 values at once, and those appear here, register 1, register 2. The ALU, you can then tell the ALU to do an add. So there's some control line tells it do an add. The add result appears here. You just kind of go, you don't really send this to memory, you sort of go around the memory to get to the result, write back, and then you write that to the register file. So that's how an add instruction propagates down this data path. Okay. So let's do a different instruction, a set less than. But this is a set less than immediate. Okay, so this is slightly different because it's an immediate instruction. And this particular instruction is set less than immediate 17, R1, write the result to R3. The first two stages are just like before, fetch the instruction, decode it. But now we have an immediate instead of a second register operand. We do a compare value. The ALU will do that operation and produce a 1 or a 0 as a result that we're going to write back to the destination register. So this is kind of similar to before. I'll go through a bit more quickly. So PC is here. Read out these values. Now, there's only 2 register operands. I'm not going to use this one, so I just mark it as an X. Instead, the second value, I'll read register 1, but I'll tell the ALU to do the comparison with the immediate value here. Okay? And remember, this immediate value, once I read it, I'm going to first sign extend it. So I read 16 bits from there's only 16 bits in the instruction encoding, but the top bit of that, I need to repeat it in the high 16 bits to give me a full 32-bit value, and that's what's going to be fed to this ALU to do the comparison. Yep, question? This one? This one? That's just adding the PC to give you the next PC for the next time around. So this, we'll see later what that's for, that path. So the ALU is doing this comparison, is register less than 17, and then that result is written back, register write stage, okay? Now let's do a more complicated instruction, a store word. So this writes a 32-bit word to some location in memory whose address is given by adding the contents of a register to an immediate from the instruction, okay? So we're again going to fetch the instruction to increment the PC, decode to determine it's a store word, read registers R1 and R3. R1 is the base address to which we'll add the immediate, and R3 is the value that we're storing at that address, right? So going through here, we read the instruction bits. This part is the same as before. So now we're taking the register base address, adding the immediate to it to get the address we send to data memory. But the data value now is going to come from this register file read port. The other register we read is now sent as data to the data memory to be stored into the memory. Right, it's another set of wires carrying the values you want to store to the memory, as well as a set of wires telling you which address you want to store it at. Okay. And notice here, the last stage is no register write back. A store is basically done when it dumps this value into the memory circuit, right? There's no register write back phase. Okay, so good question you might ask is why 5 stages? Why did I break it down to these 5 stages? It turns out MIPS and a lot of the simple RISC architectures were kind of designed around these 5 stages. It's kind of a classic breakdown. Other ISAs have a different natural number of stages you break things up into. For example, the IBM mainframe I was talking about is probably more like 7 or 8 stages would be natural for that ISA. It's a bit more complicated. It's an older ISA, dates from the 60s. Another question I have is why do you sort of say there are 5 stages if not all the instructions need to use all the stages? Because we're designing hardware, this one piece of hardware has to be able to execute every instruction, and what we'd like to do is minimize the total amount of hardware we need. So what we try and do is reuse the components across different instructions. For example, the adder is used to do arithmetic add. It's also used to do the address calculation. That's physically one circuit. And so we try and make all the instructions sort of flow through the system the same way, so we don't have to replicate hardware unnecessarily. It's like an economy by making them all look the same to the system. And in fact, in this case, there's one instruction that does use all 5 stages, which is the load. It goes through instruction fetch, decode, execute to calculate the address, memory stage to access the memory, then register write back to return the value to the register file, right? So that one instruction uses the maximum number of stages for the whole thing. And yeah, this is just going through the load instruction, how that executes. just to show you that. So, it finishes up with this. It's a broken animation. It goes through, loads the address, calculates the address, sends it to memory, gets the result, and writes it back to the register file. Okay, so load is using all 5 stages of this execution. Okay, clicker time. So the load instruction uses the most stages, uses all 5. Which of these MIPS instructions uses the fewest of the stages?
By the way, do you know how some of your news updates have been on security? Have you ever heard of the company named Norse Security?
Norse?
Yeah.
No.
Well, there's like a hint, something they have is real-time security threats.
Oh.
So it's pretty cool. Like if you want to use it, it's like
Okay.
pretty fun. Just as a comment.
Okay, thanks.
In case you run out of something.
Right. Okay. Let's see how people are doing. So, okay. All right, looks like there's pretty strong consensus there. I think people seem to have got that, so I'll just quickly walk through this. So we already said this one uses the most number of stages, so it's clearly not that one, right? Uses all 5. So the jump actually uses the fewest stages. You just have to do fetch and decode, and then you're done. So fetch, you need to go to memory, get the instruction bits, and then once you decode, you realize it's a jump, and inside that jump, the bits from memory tell you where you need to go directly. So you can just cycle that around, and you're already kind of finished with that instruction. Jump and link is similar, except that you actually have to write back the link register address, so that'll take the register write stage as well. And add, as we've seen, also uses the LU stage. So jump was the right answer in this case. Okay, a bit of administrivia. We have an exam on Thursday, in case you didn't know. Midterm in class. Everything up to lecture 8. You get a handwritten cheat sheet you can use, and we'll give you the MIPS green sheet that you've seen already, so you don't have to memorize all the MIPS stuff. Let's just take a break for 2 minutes. Give you guys a break. Okay, let's get going again. So, quick announcement. Forgot to do this. So Friday, there's a cloud event. There's a lot of good speakers speaking on Friday from 8:30 to 5 here at Berkeley. So there's a link that's on the slide. So if you want to go find out more about who's speaking, what you can do. One thing, they're looking for posters. So if some of you have done research project maybe in cloud computing already, then they're looking for people to come present posters. They're also interested in bringing your resume if you're looking for internships with cloud computing companies. But these are some of the companies that'll be there on Friday, this Friday. So lunchtime, just come along if you can't make it the rest of the day. But check out the schedule here to see about the whole event and what's going on there. All right. Back to data path and control. So this was the data path, but it does all the data transfers. But you notice there's all these signals now appearing here, and that's what the controller does. The controller's job is to tell the data path what to do when, right? And so the controller, the feedback he gets from the data path is what instruction am I doing now? And this controller then, depending on the opcode, sets all these different control lines, most of which go to something like a MUX, to set the data path the right way around to execute the instruction that's required next, right? What's interesting is a lot of CPU designers always get excited about building the data path because, how fast can I make an add or a floating point multiplier, or how fast, or how small, or how low power can I make those pieces? They're kind of fun to design. But what you find out in doing a lot of CPU design is, this is the bulk of the logic gates, and this is a tiny fraction of the logic gates. This is fun to design. This is really hard to design. So all the bugs are in the control logic because it's where all the complexity is. The data path is fun. The control is hard. So in hardware is hard. The control piece of hardware is the hardest part of hardware, right? And you'll learn that as you do the designs yourselves. But the job of the controller is to make sure the right things happen at the right time. So processor design. So when you're building a processor, you kind of go through these steps. You look at the instruction set to figure out what hardware do I need to support this instruction set. So what's the meaning of each instruction? I want to break it down into register transfers. If you have, your ISA says I have 3,000 registers, you're going to have to build some hardware that holds those 3,000 register values, right? In MIPS, you have 32 registers you have to worry about. You're going to need some hardware to hold those 32 register values. You've got to make sure that your data path can do everything that's required by all the instructions, right? So somehow your data path has to support every instruction in the instruction set. Once you've done that, you go through a design process, figure out the set of components I should use. We'll talk briefly today about clocking. Thankfully these days, it used to be in the old days, people would worry a lot about clocking and have very weird and exotic ways of clocking the circuit. These days, we have a very simple model. There's just one clock. On the rising edge, things happen. And that's the one you'll be using. You put all these pieces together, and then the next part we'll do next lecture is doing the control points and how you actually build a controller. But for the rest of this lecture, we'll start looking at just building the data path up for MIPS and how we go through this exercise of picking the right components we need. So you've already seen the MIPS instruction formats. Everything's 32 bits long, and there's basically 3 formats we worry about, R, I, and J. So there's always, the opcode is always in the same place. If you think about it, that's really good because I need to know where to start when I'm decoding the instruction. Like, where do I look first to figure out what it is? And if all the instructions have the same 6 bits, meaning the opcode, that's where the hardware is going to look first and see those are the 6 bits. They tell me how to interpret the remaining 26 bits of the instruction. You have these 3 formats. The jump type, all 26 bits are used for target address. The I type, there's a register source, a register destination, and a 16-bit immediate. And the R type has 2 register sources, 1 destination. It can also have the shift amount in here, and then a function bit that tells you more of the operations, right? So if you notice in the MIPS encoding, there's one opcode that's used for a whole bunch of different ALU operations. Because they have space at the bottom, to use this function field to tell you which of those operations you should do. So the high bit tells you it's a register ALU operation, and these low 6 bits in the funct field tell you whether it's an add or a subtract or an XOR or an AND when you're doing register operations. When you're doing register immediate, the I type, the immediate occupies all these bits. So now you need different opcodes for an add and a subtract in the MIPS encoding, right? So they try to use the minimum number of bits, but they have to be a little bit clever in how they encode those in these in various fields. So these instruction formats, this is what the hardware has to look at to decode instruction. For the purposes of the class and for the project, instead of having you implement everything in the MIPS instruction set, which might take a while, and past the first few ones of them, you're not going to learn anything more anyway, we're going to give you a simplified subset of the ones you actually have to learn. So we call this MIPS Lite, so it's just a reduced set. And so for now, let's just look at these instructions: add, subtract, or immediate, load and store word, and branch. So it's kind of one of each kind to give you a flavor of how these instructions work. So one of the things we want to do is understand what does the instruction actually mean. So when you're building the hardware, you have to be kind of precise about making sure the hardware does exactly what the architect, the instruction set designer meant. And so we often communicate that using something called register transfer language. And that just means a way of writing down what happens during the execution of each instruction. What register is updated with what value. So there's some syntax here. Just think of this as pseudocode. We're not going to give you a formal language here. It's just a shorthand for describing what goes on. So these curly braces with a bunch of fields. It's a way of saying the curly brace is a way of saying there's a whole bunch of bits here, and the elements within, separated by commas, are the different fields within that collection of bits. So when we read from the memory at a given program counter, we're going to get an opcode, RS, RT, RD, shift amount, funct. These 32 bits are split up this way, or they can be split up this way. Right, we're just saying how we like to view the 32 bits that come back from the memory at this location, right? So remember, you can think of memory as an array indexed by address, and that's the way we're going to write it in the register transfer language. So like, for example, an add U instruction, what is that? Well, register at the RD field gets the sum of these two, the register at the RS field, the register at the RT field added together. And you also increment the PC plus 4. So kind of trying to write down what is the total effect of each instruction in terms of its impact on these values inside the machine. So that's this RTL level specification of the instruction set. So or immediate, you're going to take one register operand, RS, the register whose address is given by the RS field. This RS is the same as this RS, right? Then I'm going to OR it with the 16-bit immediate field, but 0 extend. It's going to use 0 extend to say, take that value and 0 extend it up to 32 bits. Okay, so OR immediate, 0 extends the immediate, right? We also increment the PC by 4. So a load returns the value at a memory location whose address is given by the register value in the register indexed by the RS field, added to the immediate 16, now sign extended out to 32 bits. Okay? And then we still also increment the PC by 4. So a store is kind of the reverse. It stores to that location a value from the register file. It also increments the PC by 4. Now the branch is a little different because the branch compares two register values. And if the condition is true, it will set the PC to this new value, which is got by taking the immediate field, the 16-bit immediate field, sign extending it, and then the curly braces again is a way of talking about a bundle of bits, a collection of bits. And so we're putting another 2 bits at the bottom, right? So this notation, this is from Verilog. In base 2, 2 bits in base 2, 2 bits in binary, 0, 0, added to the end of the word. So we're just adding 2 0 bits, which is effectively shifting it up by, multiplying it by 4, right, to get the offset in terms of whole instructions. Each instruction is 4 bytes, right? So if the condition is not met, the else condition is just increment the PC by 4. The branch wasn't taken, okay? So it's just pseudocode for what each instruction does. Other things, what are the requirements of the instruction set? Well, we need a memory, and Actually, we really should have a unified memory, like I said, but for now, we're just going to split it into instruction memory and data memory. Keep our life simple. We need these 32-bit wide registers to hold the state of the machine, state of the program. We need to be able to read the RS field. We need to be able to read the RT field, those addresses from the instruction. We also need to write either a register whose address is given in the RT field or in the RD field. Right. We also need a program counter. We need something to hold where we are right now in the program. We need to sign or zero extend immediates. We need to do add, subtract, or OR for our LU operations. Remember, this is just MIPS Lite. There's these few instructions. We also need to add 4 and maybe this extended immediate to the program counter. So +4 for most instructions, the extended immediate for branch targets. You may also need to compare registers. Okay, so this is the going through our little instruction set, what are the operations we need to support in the hardware. So now we kind of start building up a bag of components we're going to throw together. So we're going to need combinational elements as well as sequential elements, storage elements. Remember, the combinational elements just respond to their inputs and at some time later produce their outputs. The sequential elements respond to the clock and only update their output when the clock edge arrives. So some of the building blocks we're going to use are going to be adders. So the adder is going to have, in this case, 32 bits in and out, a carry input and a carry output. Multiplexers, remember, have some number of inputs and a select signal that says which one appears on the output. ALUs have some number of 2 inputs in this case, and an operation field that says which operation to do, add, subtract, XOR, etc. Right, and it produces a result. So these are the operations we have in MIPS. Now notice that getting back to this idea that you reuse the components you have for all the instructions, the branch does a comparison. It wants to know if 2 registers are equal. And we want to kind of, instead of building it, we could build another circuit just for that purpose, right? But it turns out it'd be cheaper if we reuse the ALU to do that equality check, right? So how would you use an adder to tell, add subtract unit to tell if 2 numbers are equal? Sorry? You could use an XOR, but say you didn't have an XOR, how are you going to use an add, subtract to tell if 2 numbers are equal? Right, subtract them, then see if it's equal to 0. So you break it down into, well, I can use the subtract unit to get them a value that'll be 0 if they're equal. And now all I need is a unit that says if this 32-bit number is all zeros, right? And that's what we're going to do here. And it's on the slide. There you go. So there's a bunch of other, so we just picked a few for the lectures. There's a bunch of other operations you might add in. You probably get carried away in the project and start building out more of the whole instruction set later. So you can look in Patterson and Hennessy textbook about some more of this. So another piece we're going to need is the memory. And we've already said we're going to cheat a little here. And we're going to cheat in a big way by having what we call a magic memory, which is a real idealized memory that's kind of the perfect memory system. So this is the memory block. It has a bunch of inputs. Let's go through these. It has an address input that tells you what address you're interested in accessing right now. It has data input. When you're doing a store, you need to provide data to be written to the memory. It has data output because you need to, when you do a read or a load, you need to return the value that was at that location. You also have a write enable. So the write enable tells the memory whether it's doing a read or a write right now, right? So the one memory block has to do both functions, right? If you think about it, it wouldn't make any sense to have one memory you wrote to and another memory you read from, right? It wouldn't work very well, right? You can never read what you'd written. So this one block, you have to be able to write to it and read from it. And the write enable signal tells you what's happening right now with the memory. What do you want to do to the memory right now? The clock signal comes in, and it's only used during writes. So the notion here is that you can imagine the memory being a whole set of registers, and the address you send in tells it which register you want to access. And then at the clock edge, you're going to update that register with the new value you've written. Okay. And for now, that's a reasonable model of the whole memory. It's just a whole bunch of registers that at the clock edge, you've selected one of them to be written with the value you've presented on the data input. Okay. Now for reads, we're going to treat reads for this magic memory as being combinational. Right. So that means that any point in time, whatever address is coming in, if the write enable is set to not write but read, So if this is set to 0, and you put an address in, sometime later, the data output is going to correspond to the value stored at that address in the memory, right? That's a combinational read. But to do a write, you have to set up the address and the data, and also toggle the clock, have a clock edge come along to actually make the write happen in the memory. You can read at any point in time just by changing the address. The output will follow sometime later. But for writes, it will only actually do the write on the next rising clock edge. Okay? So you can read any time, you can only write at the clock edge. So we also need just regular registers. The flip-flops we talked about last time, but they'll be sort of n-bit wide in general. So just think of it as n copies of the same flip-flop. One little tweak we'll add is all the flip-flops will have a write enable or load enable that says basically on the next clock edge, do I actually update or not? So I can turn off the write to the flip-flop by disabling the write enable, setting it to 0. So the flip-flop will always be producing a value on its output. The clock and the write enable just control when and whether you update that value with a new value on the input. Okay. So we talked about memory and just general registers. We actually need the register file that holds the MIPS state of the machine, and we need 32-bit registers to hold those values. This is kind of like a small memory, except it has actually multiple parallel paths to it, so you can actually read two values at the same time. So you have a separate address port for register A. These 5 bits tell you which register you want to have output on the output bus A, and a separate set of 5 bits give you the address of register B. Which of those 32 registers do you want to have appear on the second read port, bus B? So you can, at any point in time, have two values coming out of that memory. You can read it twice at the same time, right, with two different addresses. And again, these are combinational reads, so any point in time you can change the inputs, and sometime later the output will represent the new value. We also can write to the register file, and we have a write port. There's a 32-bit bus coming in with data. There's a 5-bit port that says which register you want to update. And then there's a write enable signal that indicates if you want to do a write this cycle or not. And so the register you address will only be written if the clock edge rises, if you have a rising clock edge and write enable is true. Otherwise, the write will be ignored. Okay? So writes only happen at the clock edge. Reads happen at any point in time. You can read two things at once. So instruction fetch unit. So kind of building up into a slightly bigger block now. So this is the piece that does instruction fetching. So what is it? Well, it's the program counter, which is just a register, a 32-bit register holding the program counter. There's a clock that goes to that register, indicates when do I, at the clock edge is when I update the PC, right? There's some combinational logic that figures out what should the next address be for the PC, right? On the next clock cycle, where should I go? Quite often, I'll just be PC plus 4, but if you have branches or jumps, it's going to change the PC to something else for the next cycle. We have the instruction memory here, so notice the PC just feeds in as the address to this memory. The instruction word comes out. This is just combinational flow through, right? So the PC, at the clock edge, it changes. The outputs of the PC change. They go to the instruction memory. Sometime later, the output will change to hold the instruction bits, correct instruction bits of the output. So now let's look at a different piece of data path just around where the ALU is, the add and subtract pieces. So these bits appear on the output of the instruction memory. The control unit is going to look at those, decode them, and figure out how to set the data path. But if you notice, this is how I start building this unit up. We have the register file already. We just wire it to the ALU, right? So the register A port, the register B port go to the ALU. The result comes out of the ALU, goes back to the register write port here. And so the clock edge, so the start of one clock cycle, I'll read out the instruction, do the decode, set it to the ALU, it calculates the result, and gets everything set up so in the next clock edge, I'll write to the register file the newly updated result. Then I'm ready to start with the next instruction on the next clock cycle. So this is a good point to talk about clocking, right? So this CPU we're going to build first is a very simple, what we call an unpipelined CPU. Every instruction takes one clock cycle. So very simple machine. Every clock cycle, one instruction is executed completely. So you do all the phases of one instruction in one clock cycle. So when one clock edge arrives, you update the PC, and then all the signals just propagate through the whole machine to give you the results you need to update all the state of the machine, the register file, the memory, and the program counter. If they're going to be updated, it all happens on that next clock edge, right? So between this clock edge and this clock edge, all the state elements have constant values in. They don't change. They only change at the clock edge. And what's happening in between the clock edges is the signals are propagating through that combinational logic, setting up the next input to all those state elements. So when the clock edge arrives, they'll update to the next value, right? So the state only moves at the clock edges, but across the machine, there's all these wires toggling while the signals propagate through all the circuitry here, right? And so the critical path, the term critical path is used to what's the longest path through all that logic to get from beginning to end of the clock cycle. And the worst case critical path is what sets your clock cycle time, the amount of time you have to leave as a designer between this edge and this edge. If you try and go faster than the critical path, in some cases you'll get the incorrect result because you won't have left enough time for the signal to settle down so you can reliably capture it on the next clock edge. So, computer architects spend a lot of time trying to shrink the critical path so they can put the clock edges closer together so the machine can run faster, so it can do more instructions per unit time, right? That's the art of doing the CPU design. How do you make the system run fast? Okay, but this is our clocking methodology. So all instructions take exactly one clock cycle, from clock edge to clock edge. And everything in between the clock edges is just combinational signal propagation through the circuitry. Let's kind of look how this works. Let's give you a bit more of a spatial picture here. So remember I showed you those debugging diagrams, all those waveforms? Well, now you kind of get to see why you need to look at those. So here's the start of an instruction cycle. Here's the clock edge. So after this clock edge, there'll be a slight delay. The program counter will change. The output of the PC, remember that the PC is held in the register. Register's a bunch of flip-flops. Each flip-flop has a Q output. So the timing here is the clock to Q. The time from the clock edge to the output changing of the program counter. That's that little delay there, right? It'll change to its new value. Yep, question? Daniel? No, so this delay here is just the program counter value, that 32-bit register, from the clock edge to the output of those 32 bits changing. We haven't got to the instruction memory yet. Let's work through this. Okay, so program count, the new value is here. Then this new value, we have to wait for that new value to propagate through the instruction memory. Right, so this delay here is from when the program counter changes to the new value to when the instruction memory produces the instruction at that new address. So that takes some time. At this point, you have the new value of the instruction fields, like RSRT, ID, operation, function. They've all changed now to the new value at this point in time. Then you have to wait for those instruction bits to be decoded. So the control logic is just some more combinational logic. It looks at those bits, combines them using logic gates, and produces the control signals that go back to the data path. And that takes some time. So this is the delay to the control logic. And then, for example, this input to the LU that tells the LU what to do, that might be finally ready here. So all this time, this is held an old value or an incorrect value. And finally, it settles down to the correct value that tells the LU what to do. So this control signal settles down. After the control signal settles down, the delay through the control logic not only settles this signal, it'll also settle the other control signals, like this signal that tells the register file whether this instruction does it register right or not. Remember, some instructions write the register file, some of them don't. The control logic looks at the bit patterns in the instruction to determine which one's which, and that's the value it sends down on this wire to the register file. That takes some time as well from when the instruction bits are ready till you know whether this instruction writes the register file or not. Now, another thing that's going on in parallel, actually, is that once you get the instruction bits here, we're feeding in the, well, it takes some while to figure out which registers we're going to read. We feed those into the register file to access the register file. And then finally we get the right values out on the output of the register file. Then those got fed through the ALU. The ALU does the computation during this time point. And finally we have the new value ready to be written. It's all set up and ready to go. And we still have to wait a bit longer for the setup time of the register file, right? The register file is a bunch of registers. You have to wait till it's ready to be clocked. And then finally you clock it. And what happens on this edge is that the add updates the register with the result, but also notice at the top here, the program counter has now moved to the next instruction, right? So the state of the machine in the register file represents the completion of this instruction, and the program counter now points to the next instruction. So now you're ready to repeat the whole cycle for the next program in the system. So basically that's how the whole thing works. You little state machine reads instructions from memory, computes the results, updates the state, and is ready for the next instruction. That's basically the whole computer processor right there. Very simple design. That's all you need to build computers. There's a few more details we'll go over next time, especially how you build the controller. But that one complete cycle, that's the part of this very simple machine. And like I said, this can run any program you can write. Maybe a bit slower than the IBM machine, but it can do anything the big computer can do. So this is putting together more of the whole data path. We'll go over this in more detail in a week's time, next week. So good luck on the midterm.